Welcome back to I Can Science That and our continuing analysis of the solstice observations. Last time we did the flat Earth analysis. Today, let's see how this works on the globe. We were going to use these data to calculate the radius of the Earth, and in fact, we were going to confirm whether or not it is actually a sphere or perhaps some other shape. Let's get into the data and see what we got. What I'm going to do here is, I'm just going to use the same tab. I'm going to create a new column here for the globe radius. And that'll be in kilometers. Everything's in kilometers. Okay, I'm going to use the same pairs that we chose last time. Keep it fair. What are we doing here? Like I showed in the previous video, I'll link that up there. The math behind this is that we are presuming that the sun is very far away here, and then we are going to calculate based on the distance between a pair of observations and the angle between those observations how big the radius of curvature must be if we approximate that section of the Earth as a sphere. What would that section's radius be? And we're going to go through these different sections and see how does the curvature vary. Okay, so what was the math for that? We're going to need the distance between the sections right there, and we'll divide that by the difference in the angle, and that's in radians right there. Okay, so the first section, we got 6,523 kilometers. 6,523 kilometers. Let's take a look at the next section. Next section, 6,203. And the next section, 6,266. And then this last one is from the farthest north to the farthest south. What does that one give us? 6,335. So we have some variation. We do have a little bit of variation, but I think it's immediately apparent that the amount of variation is dramatically different from what we saw last time when we looked at the flat Earth numbers. They were all over the place, varying from 5,700 to 1,460. Here we have things that are varying by a much smaller amount. Let's take a look at that as an error away from the accepted globe radius. Let's do that. Let's say error, and let's make it as a percent. So Earth radius, kilometers. Apparently, we're supposed to get 6,371. Let's see, what did we get? I'm going to say equals that number minus the 6,371 quantity. Let's take, I want it as a percent, so I'm going to multiply by 100. I'm going to divide by the correct answer. What did you do? Oh, this commas. It doesn't like the commas. Okay, so the percent of this first observation there is off by over 2%. That's not bad, right? That's not bad. 2%. How about here? We're under by 2.5%. And then this one is 1.5%. And on the big one, wow, the big one is 0.5% off. So our calculation of the radius is right up there with what Eratosthenes supposedly did, if you believe those stories. And even if you didn't, what did we find? Well, our observations have confirmed what Google just told us about the radius of the Earth is fairly consistent throughout the shape of the Earth, and we are within less than 3% off from what that told us. Let's go take a look at the visualization now. I have a visualization. Let's look at that. Very similar to what I did yesterday. I have a Python program here where now we're going to look at that exact same data set, only we're going to look at it from the point of view of the globe model. This is our globe. This is the Earth here as a circle. The radius is indeterminate at this point. It doesn't matter what the radius is. We're just looking at the raw data. And then what I will do is I will show this is the North Pole and the South Pole, and then this line here represents the equator, and I just extended it out just so you can help you see what's going on. So our first observations are from the southern hemisphere, and let's take a look at those. So there we go. There's our first observation from down south, New Zealand way, and they found that the sun was somewhere north at that angle. Let's see the rest. As we continue up further north, we find more generally just sort of pointing in the same general direction. Let's pop over the equator and see some northern observations there. What have we got up there? Those red ones, remember the red ones are off by over 2 degrees. So yeah, there's a little cockeyed, but let's go. There's some green ones. Oh, there's a red one. Look at that. There's our big error there, and you can see how far off that 3 degrees really is. And a bunch more observations. So let's look at all of them, all the way up to Finland, where we have, this is our data set. So you can see, I think, by looking at this, how ancient peoples who did this sort of observation would definitely have come to the conclusion that this model makes a lot more sense than that flat model. Like in the flat model, this data was every which where, and we'll need to start talking about how refraction can maybe help us make sense of that or something. But with this model, the data makes sense all by itself. We don't need to start inventing new concepts and applying refraction. Now we know there is refraction. And the question that I asked last time about the data was, how much refraction do you need versus how much refraction are you willing to accept? Let's ask that same question here with this data set, and honestly, the amount of error that we're getting, just the disagreement between adjacent measurements, is more than any amount of refraction that's required to straighten this whole thing out. So we do not need any refraction to sort this out at all. 0. So this model is fine. It works fine with 0 refraction for all of these data elements. And that is because the amount of accuracy, the level of accuracy of these measurements, these are just regular people in their backyards. So some of them are off by 3 degrees. The amount of refraction that we expect, according to understood science, is less than a degree. So if we have measurements off by as much as 3 degrees, then 1 degree here or there caused by refraction is going to get buried mostly underneath just the measurement error. And by the way, that is what the globe model calls for, is less than 1 degree. And in particular, for these angles, which are all of these angles are well above the horizon, the amount of refraction in those zones is generally considered to be negligible, very, very small, certainly immeasurably small within the error tolerance of our simple measuring setup. As far as the globe Earth hypothesis, what have we achieved? We have achieved confirmation that the model makes sense. We have also confirmed that the radius of the Earth to within 3%, and we have found that it doesn't vary much. And so that tells us that the overall shape that we just observed with our measurements is in fact a sphere. We didn't just assume and confirm it. That's what this visualization is. But what we did with the measurements is we measured what the radius appears to be at different sections. It appears to be fairly consistent. Because of that, a consistent radius, that's the definition of a sphere. So we measured it to be a sphere, and we measured the radius of that sphere to be very close to what the textbooks tell us. So good job, everybody. I hope we all had fun with this. After this, let's see where the comments take us. I have a feeling that we're going to want to talk about how the refraction can be applied to that flat Earth model. Because, you know, if you are a hardcore flat earther, you're not ready to just give that up just because of this. If you are a hardcore flat earther and you're still wanting to cling to the flat Earth model, that's okay. All I ask is that you start to understand where we're coming from. That we're not out here faking things and deliberately trying to lie to you or fool you. We are not being morons. We are not completely had the wool pulled over our eyes. We are not taking it just on faith. We did this experiment and we see this result. This result leads us to the natural conclusion that looks like the Earth is a sphere. If you want to continue to tell me that the Earth is not a sphere, all I ask is some kind of evidence to support that, because the evidence we collected ourselves so far matches up with the sphere. Now, that doesn't mean that there's no possible way it could be flat. We can keep talking about that. All I'm asking is that you understand that we came at this with an open mind. We did an observation. We collected data ourselves. This is not indoctrination. This is not trickery. This is just what the data looks like. And the data, I hope you can understand how we would be led to believe that the Earth is a sphere. Even if maybe you're not ready to accept that yet, that's okay. But this data makes it look like it is. Let's have that conversation respectfully down in the comments, and let's see where that takes us. We can investigate this deeper. We can move on to the next topic. You guys can guide this conversation and see where this goes.